Now we move on to the RC differentiator. We'll start again with the single pulse. In terms of time response, a series RC circuit in which the output voltage now is taken across the resistor is known as a differentiator. Recall that in terms of frequency response, it's a high-pass filter. The term differentiator is derived from the mathematical process of differentiation, which this type of circuit approximates under certain conditions. So the figure below, RC circuit, is an RC differentiator and a pulse input. So we've got a square wave generator on here. We're going to give it one shot. The same action occurs in a differentiator as an integrator, except the output voltage is taken across the resistor rather than the capacitor. The capacitor charges exponentially at a rate depending on the RC time constant. The shape of the differentiator's resistor voltage is determined by the charging and discharging action of the capacitor. So we're going to see the output waveform looks a little different from the integrator, where we have lots of area under the curve. Now we're going to see a more spiked type representation by the exponential charge and discharge of the capacitor. To understand how the output voltage is shaped by a differentiator, you must consider the following. The response is the rising pulse edge. The response between the rising and the falling edges, and finally the response to the falling pulse edge. Let's assume that the capacitor is initially uncharged prior to the rising pulse edge. Prior to the pulse, the input is 0 volts. Thus, there are 0 volts across the capacitor and also 0 volts across the resistor. So, we can see here, again, a representation of that circuit and how we're going to take the output. So if we look at this step by step, we can see that we have the initial state, uncharged, nothing happening in A. In B, we input a square wave, one shot, voltage in, going min to max, 10 volts, and the capacitor at this point is not charged, it's sitting at 0 volts, and nothing has happened, nothing is going on at the output. Okay, in terms of the capacitor charging or discharging. So at this point we have that transition between minimum and maximum occurring. So now in C, during the level part of the pulse, when the pulse width is greater than or equal to 5 time constants, we can see the capacitor doing its normal exponential charge here is moving toward 10 volts. Recall that we have to have at least 5 time constants in order for the capacitor to achieve its maximum charge from the source. So at that point, you can see what happens at the output. The output then goes from its maximum transitioning to its minimum. So at D, we can see the falling edge of the pulse on the input. Okay, so we have our charge at over the capacitor, and then we have our discharge going from minimum to maximum. The output then is now at 0 or minimum and dives to negative 10 volts and starts charging back up. So during the pulse width, the 10 volt pulse width, you can see what happens here, and they just chose some arbitrary value of 5 volts, okay, just to demonstrate what's going on. You can see what happens here, that the transition now is from 10 to 5 volts, and then during the falling portion of the input, when it goes from maximum to minimum, making the transition, we end up with 5 volts to minus 5 volts, and then the charge occurring again. So the response of the rising edge of the input pulse then looks like this. Let's assume that the 10-volt pulse is applied to the input. When the rising edge occurs, point A goes to plus 10 volts. So we need to keep going back to these representations as we look at the reading here. Recall that the voltage across the capacitor cannot change instantaneously, and thus the capacitor appears instantaneously as a short. Okay, so that's what's going on here. There's no instantaneous rise. Okay, you can see that it is actually exponential. Therefore, if point A goes instantly to plus 10 volts, then point B must also go instantly to 10 volts. Okay, so we can see that here. We've got 0 to 10 volts corresponding to the 0 to 10 volts at the input. This keeps the capacitor voltage then 0 for the instant of the rising edge. The capacitor voltage then is the voltage from point A to point B. Okay, so we're talking about the output here from across the output here, across the resistor, point A to point B. The voltage then at point B with respect to ground is the voltage across the resistor and the output voltage. Thus, the output voltage suddenly goes to 10 volts in response to the rising pulse edge, as indicated in B. So here we are in B. It goes from 0 to 10 volts. The response then during the pulse width, when the width is greater than or equal to 10 time constants, while the pulse is at its high level between the rising edge and the falling edge, the capacitor is charging. So the capacitor here, you can see in C, is taking on a charge exponentially, and we are moving through the pulse width of 5 tau. When the pulse width is equal to or greater than 5 time constants, the capacitor has time to fully charge. Okay, so this is a fully charged capacitor we see here in C. As the voltage across the capacitor builds exponentially, the voltage across the resistor decreases exponentially until it reaches 0 volts at the time the capacitor reaches full charge. Again, after 5 time constants. So you can see the capacitor is charging to full. The resistor output, or the output taken across the resistor, is going to 0. That can only occur when we are at 5 time constants or greater. This decrease in the resistor voltage occurs because the sum of the capacitor voltage and the resistor voltage at any instant must be equal to the applied voltage. This is in compliance with Kirchhoff's law. So V sub C plus V sub R equals V in. This part of the response is illustrated in C. So now we move on. Response to the falling edge when the pulse width reaches or is greater than 5 time constants. Let's examine the case in which the capacitor is fully charged at the end of the pulse greater than or equal to 5 time constants. So we refer to D. So now we're down here looking at what happens then. Capacitor is fully charged. We have gone the entire length of the pulse width and the capacitor is discharging. So we're on this falling edge of the input. Look at what's going on the output here taken across the resistor. On the falling edge, the input pulse suddenly goes from 10 volts back to 0. An instant before the falling edge, the capacitor is charged at its 10 volts. So point A is 10 volts. Point B is 0 volts. The voltage across the capacitor cannot change instantaneously. So when point A makes a transition from 10 volts to 0 on the falling edge, point B must also make a 10 volt transition from 0 now to minus 10 volts. This keeps the voltage across the capacitor at 10 volts for the instant of the falling edge. The capacitor now begins to discharge exponentially. As a result, the resistor voltage goes from -0 to 0 in an exponential curve. So we can see that here. We're going from -10 to 0. So if we look at then the response during a pulse when the pulse width is less than 5 time constants, when the pulse width is less than 5 time constants, the capacitor does not have the time to fully charge. Its partial charge depends on the relation of the time constant and the pulse width. Because the capacitor does not reach a full 10 volts, the resistor voltage cannot reach 0 volts by the end of the pulse. Okay? The next step then is response to falling edge when the pulse width is less than 5 tau. Let's examine this case where the capacitor is only partially charged at the end of the pulse width less than 5 tau. If the capacitor charges to 5 volts, the resistor voltage at the instant before the falling edge is also 5 volts because the capacitor voltage plus the resistor voltage must add up to 5 volts. So go back and read through these and follow through what's going on in the circuit depiction here and the signal depiction as you move through each of the states from min to max, max to min, and then the case where you do not allow the capacitor to fully charge. Okay, so a good way to summarize this section is to look at the output waveforms of a differentiator as the time constant is varied from one extreme when 5 tau is much less than the pulse width to the other extreme when 5 tau is much greater than the pulse width. These situations then are shown in the graphs. So if you step through these, you can see then in each case as we change the time constant what the output waveform is going to look like.